a little bit relaxing now. So we want to acquire high resolution anatomical data. And I want to start off why we want to do this and then how we can do it on the 70, and then I show some beautiful images of vasculature. So why do we acquire the data we acquire for structural imaging? And when we do laminar fMRI studies. And the reason is we want to know where in the brain we are, in which cortical area and in which depth. It would be nice in a perfect world if we could just acquire a really high resolution anatomical image, as for example Falk Lüsebring from Magdeburg did, and then we zoom in and we see nothing. There are no layers. And that's very unfortunate that MRI contrasts are not sensitive to cell density or the type of neurons you see in different layers. So usually your T1 is pretty homogeneous across gray matter. Just as a reminder, gray matter thickness varies quite a lot, layer thickness varies a lot, but we should be able to pick something up here with the really high resolution acquired, but yeah, there's usually not much to see. There are always exceptions. So this is a study from Natalia Petridou's group, and they kind of like tweaked the protocol to make the difference between gray matter and white matter highest. And why did they do that? If you remember, for example, in visual cortex, we have this trio of generi. So these are highly myelinated layers. And you might know that myelin actually has a T1 effect. So and that's why kind of like white matter is, white, because there's a lot of myelin in there. And if we zoom in, you can see, I would say, let me turn on my, there we go, my pointer. You can kind of like see here, there's definitely something. So it is possible to image some layer features using MRI. Is this something you would routinely do to help with your layerification for your laminar fMRI study? Probably not. This is probably not giving you a lot more information than what you would just get by, getting your gray matter, white matter border, your gray matter CSF border, and just, put in the layer based on your anatomical knowledge. I think this might be interesting if you're working in a clinical population where you expect that for some reason their layer structure looks different than what it usually does. But otherwise, what we're actually trying to get is CSF, gray matter, white matter. And based on that, we can then, draw our two main partitioning axes of the cortex. So one is kind of like the laminar or depth-dependent direction, which is perpendicular to the surface. And the other one is kind of like parallel to the surface and usually kind of like the columnar orientation. And this is kind of like bread and butter MRI. One of the most commonly used sequences is MP-RAGE. It's a T1 weighted contrast. It's very often used at 3T, and it basically consists of a magnetization preparation module, then a readout, and then some recovery time. And if we zoom in into the sequence diagram, we can see the magnetization preparation is a 180-degree pulse. Then we wait a little bit to let the magnetization recover, and then we have our gradient echo readout. And this is basically the inner loop, and we then repeat this until we have filled off all of our 3D K-space. So this is also a 3D sequence. But basically the difference here is you see kind of like we have many different little flip angles. So instead of, going through K-space in one go, we take every line individually. So this is kind of like a slow sequence, takes a couple of minutes to get one image. But of course it has kind of like really nice quality, and we get to much higher resolutions, obviously. There's one kind of like thing I want you, or John wants you to be aware of, which is T1 blurring. So as we go through the kind of like inner loop, the signal still recovers. And the trick is to kind of like find a balance. So you basically get, kind of like the difference between gray and white matter while you're reading out your case space. If you don't do this very well, you basically introduce blurring, because you can see that the signal changes over your readout times. And that as the T2 star blurring earlier in EPI puts a filter onto your case space, and on the right you have kind of like a worst case scenario. So we have white matter. This is a simulation, by the way. So white matter with kind of like a higher intensity than gray matter. And now they basically put one gray matter voxel into white matter and one white matter voxel into gray matter. And due to T1 blurring, they end up with exactly the same frequency, the same intensity. So if your segmentation is purely based on intensity, you can't tell white matter and gray matter apart anymore. So it's always important to keep your inner loop as short as possible. For example, through using grabbar there, to just make sure that this resolution you set at the scanner is actually the actual resolution you get out of your images. However, most or all of us do laminar fMRI at 7T. And that brings quite a lot of challenges to most T1 rated imaging. One is simply the longer T1s, which means we have longer delay times, which means we are less efficient. Then all the B1 and B0 issues. So we have lower inversion efficiency in areas with low local B1 plus, or with very large B0 frequency shifts. So that means our T1 contrast varies quite a lot. And you can see that here, right versus left, that's not the same intensity. And kind of compared to EPIs or fMRI images, where we always take the difference between activation and rest, here we need a homogeneous contrast. So if your EPI image looks a little bit funky, that's okay, as long as it looks the same or has the same inhomogeneity between the two conditions. But in structural imaging, we want to have a homogeneous contrast. We want every voxel that is gray matter have exactly the same intensity across the brain, because that's how we basically use or do segmentation to say, this is the intensity that corresponds to gray matter, so this is a gray matter voxel. And you can see if you run an MP-RAGE image on the 70, that doesn't really work anymore. So here at the front, we have some really bright spots. And if we zoom in, just to, you've seen it on the slides a couple of times, B1, but basically because the frequency goes up, we have kind of like constructive and destructive interference of the RF pulses. And one of the first images acquired on a 70 looked like something like this. And people were very disappointed when they saw it, because everyone's like, oh my gosh, the first 70 images. And it looked really bad. It has this really central bright artifact. And this is basically just a constructive interference of the RF. It just gives you a lot of signal in the center and not a lot in the outer areas. So most sequences now correct for that. Also to keep in mind that basically your flip angle that you set at the console is not the flip angle that you get usually. So these are some measurements, and you can see that maybe not quite zero, but it can vary a lot across the brain what's the actual flip angle you are getting. And so this is a challenge we have to deal with at high field, ultra high field. And if we zoom in, we will look at this artifact again, but just because I also had a project with frontotemporal dementia, and the temporal lobes are very often, can you see that, it's just cut off? Is that coming clear? That's probably where it doesn't project. So basically, you see how, the black or you have the white matter here, and there should be a gray matter around it, but it's gone. Yeah, so this is B0. And basically, you don't have a good inversion efficiency anymore at that point. which is a problem if you, for example, study people with FTD, because they are also the disease means that the gray matter is gone. So you don't know which one is it, which can be quite challenging. And the other one is B0 distortions. I said we have, very high bandwidths, nice image quality, but we are also talking about a different spatial scale. So now we want to, make decisions about maybe 50 microns, 100 microns, which means now even tiniest distortions coming in through the readout can play a big role. So be aware of that as well. So what have people done to deal with these issues, especially the kind of like B1 issues? There are two sequence types. One is MP2RAGE and the other one is MEMP-RAGE. So MP2RAGE acquires two flash or gradient echo images after each other, but with a different inversion time and a different flip angle. Oh, sorry. You can see here, you basically just repeat this readout module again, but obviously at a later time and with a different flip angle. You then get two contrast. So this is the magnitude and the phase of the first, and this is the magnitude and phase of the second image. And then you can combine them in this kind of like complex way. And then you see you're kind of like getting rid of a lot of these inhomogeneities. So MP2RAGE basically removes all the dependence on M0 or proton density, T2 star, and B1 minus, and is only weakly dependent on B1 plus. So it gives you kind of like, nice homogeneous contrast across the brain. But you might say, oh, there's all this noise in the background. That's really ugly. And if you put that into FreeSurfer, it will just not work at all. So they worked on removing the numerical instabilities during the division. And basically they tweaked the formula a bit and added kind of like this regularization factor. And that means that if like both the term on the top and the term on the bottom go to 0, which is the case where I get kind of like this noise amplification, then it no longer goes to kind of like crazy numbers, but it goes to minus 0.5, which is basically black or the background. And you can tweak this regularization factor if you want. And it works quite nice. So if you look here, basically all this ugly noise is removed. If you have some really old images that don't do this on the scanner, there is some code from Jose Marquez on GitHub where you can put in your like both inversion images and the combined image, and it will do this for you. So these are just the kind of like MP2RAGE specific challenges. One is the nonlinear tissue contrast. Due to this kind of like complex combination, there is not, if you have a voxel that's 50% gray matter and 50% white matter, it's not going to be in the middle of these two intensities. It's going to be somewhere else. So that's something you can kind of like take into account. I find that the field has just agreed to ignore it and move on. And protocol optimization is actually pretty tricky. I would say it's in some ways trickier than a 3D EPI. There's less intuition about things. Yeah. And if you come across TR foci, so this is a form of RF pulse that is built to be less, so it's an adiabatic pulse and it's built to be less sensitive to B1 plus issues. So if you come across these, I think they're now more or less standard in these protocols. I would say kind of like maybe 5 years ago or 10 years ago when this started, there was a lot of which pulse should be used, but now it's like solved or people have decided on something. So yeah, Jose was very kind and has shared me some of his MATLAB code to actually optimize. So this is more or less what he had in the paper. So you basically put in number of slices, how long can like each individual readout of the gradient echo takes, and what is your assumed T1 of CSF, gray matter, white matter, because you can obviously do this for different field strength. And then it kind of like puts you out, okay, what's your TR, what's your inversion times, what's your flip angle. Maybe you're like, oh, Saskia said I should, shortening my inner loop, so I'm adding 6/8 PF, Grappa would be actually better, but in his simulation, he had partial Fourier. So let's do that. And oops, everything changes, right? So if I go back and forth, you can see all the numbers change for basically the optimal CNR. So this simulation estimates what's your maximum CNR across kind of like these 6 parameters. So TR, inversion time, inversion time, inversion time, and the 2 flip angles.
What are the colors? You said.
This is a scaled CNR, theoretical, sorry. Yeah, this is scaled CNR. So yeah, red is obviously highest. And so this, and you can see it's kind of like quite a complex relationship between all these two. So it's not, and also because, it's 5 parameters. If you just want to kind of like iterate your way through all of them, you're acquiring a lot of images. So be mindful. I think another thing, obviously, if you say, oh, you know, I'm doing high resolution fMRI, I obviously should do high resolution structural imaging. So I'm getting more slices because I'm making them thinner. And again, you can see that all of these parameters change again. If you're like me and you've just read the current or the newest book on ultra high field imaging, then they had very different T1 values in there actually. So I used these and went back to original protocols, boom, different parameters. So, and obviously this is all under ideal circumstances. We haven't talked about, you know, kind of like how the image contrast change if your B1 is not where it's meant to be. If you're not getting kind of like full transmit power. I mean, as I said, he's not fiddling a lot with it. I know John fiddles a lot with it. So it depends, but you have your own coil, so that's quite different. But obviously these parts need a lot of power. So what I'm trying to say is this is not easy either. So if you want to change it, put in enough resources to make sure it still works. If it works for you, don't fiddle with it. I have, unfortunately, or we've all, I think, witnessed very bad cases where people thought, I can just, you know, make my sequence a little bit faster. I'm here, why is the TR so long? That's a waste of time, and just make it more efficient, and completely screwed up the contrast. So yeah, keep in mind not to, I think on a 3D API, you know, you want to, you know, optimize for your research question on this. If you have a good protocol, stick with it. MemPrage is, I think, a favorite here. It basically has a higher bandwidth, so less distortions. And this is because they put in a multi-echo gradient echo readout in here instead of the one single echo. But it requires more inversion pulses than MP2Rage, so it means even more SAR requirements. What are in general challenges? And this applies to MP2Rage and MemPrage the same. So one is this Dura has very similar intensity as gray matter. I don't know, did anyone mention in the structural and the anatomical lectures Dura? No. So Dura is like a really, really thin skin that's kind of like on top of the skull, if you're not familiar with it. And it kind of like, you know, so protects the brain in a way. And you can see it here. It's sometimes, you know, far away and detached, but there are also places where it really sits next to the gray matter. And these are places where you can't distinguish, or very often you can't distinguish the Dura from the gray matter. So your segmentation might kind of like include that, although you know probably one line of voxels is actually Dura. And the other one is kind of like the low B1 plus in the temporal lobes. So here you can see it again that we know that this should probably go more like this. But yeah, kind of like simply you don't get a good inversion, which means you don't get a good signal here. So if you're interested in the temporal lobes, it's actually quite a challenging area to do T1 imaging. Another one is you also get inflow from arteries. And this can also kind of like screw up your segmentation. So you get kind of like little humps I don't know if Doug is going to talk about the correction he put into it. Probably not. I know I bugged him about this and he said he did something about it, so I'll ask him again, but this is also kind of like an extra challenge. So what can you do? One idea is to use multimodal imaging, and you basically add a T2 star weighted image for better segmentation performance. So here you have the example of the dura, and here you have the example of 2 vessels. Can you see that? Oh, it's a little bit tiny. And if you have the T1 weighted image alone here, the dura is included, and you can also see here the vessel is included. Whereas if you add a flare, which is a T2 weighted anatomical image, you get quite nice separation. The only problem is getting good flare at 7T. So you're basically changing one problem for another. So I think at the moment, many people just do some manual corrections on their surfaces, unfortunately. MP rate works pretty well or just doesn't work at all, depending on how lucky you are. And some of you might, well, I don't have these problems at 3T, why I could just go to 3T and acquire my structural images there. And there are a lot of advantages. So as I said, you have the homogeneous contrast, less bias, less inflow, and FreeSurfer loves 3T data. That's what it's made for. So it all works really well. There are a couple of buts. I mean, one is just the practicality, bringing people in several times at different scanners. You have different distortions. So I'm here talking about gradient nonlinearities. So basically your gradient chords, they're meant to kind of increase the field strength linearly across space. And that works really well up until the edges where it kind of like flattens off. So that means that the top and the bottom, which is really the neck, they get kind of like compressed. And that depends on the gradient core you have. And that is obviously different between 7T and 3T. Then you have to register an image that's kind of like in a completely different position than all your other fMRI images onto these images with an accuracy of, I don't know, 100 micrometers or something. Then you have time of day effects. So the brain changes, minusculely, depending on what time it is, how much water you had, and all these things. So there's also not the same brain in the scanner than there used to be like the day before where you did all your functional images, and your practicalities. Another point I wanna, or something else John actually mentioned is, don't go too crazy on your structural images. Don't think I wanna resolve layers. I need to have like 500 micron resolution. That's not why we're here. We just want to distinguish CSF, gray matter, white matter. If you don't have enough residue, or if you don't have enough SNR, which comes from high resolution data, your segmentations will not look particularly good. So here they averaged 6 images and suddenly looks really nice and smooth. But think about if you can basically, get away with higher resolution, then you don't have to worry about SNR so much. Yeah, I think that's kind of like it I want to talk about for structural imaging. On the one hand side, it's kind of like bread and butter what a MRI scanner does. On the other hand side, it's kind of like challenging to actually, utilize it for our purposes. So put a little bit of effort into it, but also, once you have a good protocol, you can kind of like stick to it. I think it's not something you want to optimize for every single, new area of interest probably, but that's something that, you can maybe put together as a center or a team, like, okay, this is our T1 protocol, and that's how we do it. We have heard that obviously the vasculature is quite important for our fMRI signal. And some people might say, oh yeah, let's have a look at the vasculature and just see, what's happening, how it is contributing. And most commonly, veins are imaged using susceptibility weighted imaging, or SWI. It's very common in clinical application. It kind of like mixes magnitude and phase contrast. In I would say, unpredictable ways. So you can see that, yes, the vascular contrast is actually quite nice. You can see kind of like these small veins in the gray matter, and you can even like see here, intracortical veins. So it's pretty good. But what it does, it kind of like takes this processed phase and multiplies it with your magnitude image. And you can see kind of like around really large vessels, you get this kind of like massive contrast change from basically white to black and then to gray, or sometimes even, white, black, gray, exactly. So this makes it kind of like, I would say, an unfortunate and not very suitable contrast if you think about segmentation. So if you kind of like want to know, or if you think, oh, I acquired a venous vasculature, and then I, kind of like just segment where the veins are, and then I look if this is next to my activity, then this is not easy, because you can see kind of like how it, starts to be blurry. So vein should be kind of like really well defined, kind of like round object. But here it kind of like gets all these smudges, and then you have also kind of like this white stuff, which you know what it is. And also here, the other problem is your CFS is black and your veins are black. So all the veins that are really on the surface of the brain are black on black. So you don't see them at all. So I would not recommend to use SWI if you want to image your veins. What you can do is something even simpler, which is just a multi-echo gradient echo. So this is some of Farouk's stuff. Obviously, you want to go to fairly high resolution. I think that 30 minutes actually not true. It's actually 60. So it takes a long time. And it's a kind of like a really, it's kind of like, no, I think spin echo was, at least in yeah, exactly. So what's, so how long is one? Yeah, yeah, but okay. Yeah, so 60 minutes for one session for one slab. Yeah. And this is kind of like one of the most simplest sequences you can do, but I like it because you have, I would say, kind of like actually similar contrast compared to SWI. It's good. We also see kind of like intercortical vessels, but you can see, for example, this is the sinus, the sagittal sinus. So you can see that it's actually well defined. It's not kind of like mixed in with the background. And you can also segment these really, really large veins quite well, which, for example, if you do lots of visual imaging, then you have kind of like the transversal sinus at the back. So that could be a problem for you. So I think that is a kind of like a bit better technique if you think more about kind of like processing the data. If you really just want to visualize veins, then SWI is okay if you look for whatever anomalies. But if you start to kind of like process the data, it's quite nice. And this is an example where Farouk basically took this data and then flattened it, which he will describe tomorrow. And you can see kind of like all these little black spots. These are draining veins. So this means we're actually getting into an area that's really, really interesting for fMRI, because we said this is where some of the main confounds are coming from. And for comparison, we have data from Duvanois next to it. So this is ex vivo data, and we can see, we're obviously not seeing every single vein, but we are seeing the big ones. And I think that's pretty exciting. Time of flight imaging is the counterpart to that. So if you want to see the arterial vasculature, again, pretty high resolution, long acquisition times, but it's possible using, I would say, common sequences. And you can do some really, really, really nice analysis with it. So this is basically taking the segmentation, smoothing it, extracting center lines, scaling the vessels according to their diameter. Then you can also look for branch points and endpoints, and basically get a little bit of quantitative information on your vasculature. So to conclude, there are dedicated sequences to deal with the problems we have at 7T to get a reasonably homogeneous gray matter, white matter contrast, except in the problem areas that I mentioned. It's either an MP2 rate or an MP rate. As I said, you spend some time to optimize your protocol, but also keep in mind that all these parameters are interrelated. And T2-star images can help to deal with Duran vessels, but they're also, again, quite tricky to actually get at 7T. So I don't think the field has really found a working consensus on what to do. And yeah, oops. So high resolution is not useful without sufficient SNR. So I've unfortunately witnessed that recently, that someone thought, oh, I need to go to 0.5 to properly resolve the layers or the borders, and they have to just spend hours on correcting the segmentations because they don't have the SNR to actually do that. So here, higher is not always better. And you can do vascular imaging using, I would say, optimize the high resolution sequences, but they are common. So it's not like you need some crazy new sequence type someone put together. So these are all pretty common product sequences. But basically the tweak is the resolution and a little bit of protocol optimization. And this is, again, some beautiful images from Farouk. But you can see that even then, you know, the arteries look really, really nice. They're kind of like round structures. And the veins are good, but they're not perfect yet. So it's actually, I think, trickier to, you know, get a really nice image of a vein. It's very easy to see them because through the bold effect, we're actually sensitive to smaller veins than our voxel size because we have kind of like these extravascular contributions again. But that also means they're not really the shape they should be, which also makes kind of like estimating diameter again more difficult. But I think it's definitely, you know, interesting, or might be worthwhile for you if you're interested to get an idea kind of like what's the vascular surrounding of my activated area. With that, yeah.